surprised to see that feedback, but I thought it was something. I guess so, yeah. Okay, good job, but apparently, I guess you didn't care about the name.
Okay, let's get started. So, I have released both Homework 4 and Project 4 on Monday. They're due roughly in 2 to 3 weeks from now, right before Thanksgiving holiday. And the plan forward is that I plan to finish the discussion on pre-evaluation this week. We're gonna spend just a little bit more time on single table evaluation. We're almost to the end of it. Then we'll start talking about multi-table evaluation, mostly joins and things like that. Then that will be Thursday's lecture. Then next week, on Tuesday, I will spend one lecture on query optimizer. Then we're done with query evaluation and optimization. Then we'll move on to the last major part of the course, which is transaction, which is a major component for database system and a major reason for the success of relational database system, which you will understand why when we come to that. Hopefully we will be able to finish the discussion of transactions by the end of November, including crash recovery and concurrency control and things like that. Then we have 2 or 3 lectures more in December, which I will use for discussion on NoSQL system and branching out a little bit, go beyond relational database system. And you will have one more, besides Homework 4 and Project 4 that I have already released. You will have one more project and one more homework. The one more project will be implementing the join operator. And then one more homework will be on transactions. Then we're ready for the final test. For those discussion I will have in early December on NoSQL and things like that. I will not test them in the final exam. So those will be just some, discussion to broaden the scope of this class and to make you understand better, with the knowledge and skill you have learned from the design and the implementation of relational database system, how that can help you go and design and use systems that are not relational based. Go to feel comfortable of using NoSQL systems. Okay. That being said, let me. What I'm gonna do today is I'm gonna, like I said, finish the discussion on single table evaluation. Then before I move on to the multi-table evaluation, I will 5 minutes briefly explain Project 4 a little bit. Project 4 is rather straightforward, so it's much easier than your Project 3. If you ask me how difficult it is, it's probably on par with your Project 2. Maybe I think it's even easier than Project 2, than Buffer Manager. But I will spend 5 minutes explaining what it does and the API of Project 4. Okay. But before we do that, let's finish the discussion on single table evaluation. So last lecture, towards the end of the last lecture, we are almost done with single table evaluation. We talk about, sorry, this is multi-table evaluation. Single table evaluation. So we are right here. We talk about how we can use hashing to implement group by and aggregation, right? To give you a little bit of context, we were talking about group by aggregation. So you do a group by over a single table. There's no join involved, right? So it's group by over a single table, and then you do an aggregate per group you have produced by the group by clause. And the question is, how do you evaluate this in the database engine? And we said you can use this hashing-based approach using this, what we call a two-phase hashing algorithm. Quickly, we finished discussing this, but quickly recap what we have said. So there is a partition phase and there is a rehash phase. In the partition phase, you use a partition hash function called HP that reads one page at a time from the input table. That reads into this input buffer. Then you apply the partition hash function HP over this page of data in the input buffer. which will push this data to b minus 1 bucket. Supposing buffer size is b, right? You use 1 for the input buffer, you are left with b minus 1 output buffers. So the range of your hash function is from 1 to b minus 1. And this partition hash function will push data into one of those output buffers. Whenever one of the output buffer is completely filled, you dump that to the disk. Okay, you dump that to the disk. And on the disk, you maintain b minus 1 partitions, one for each output buffer. So the first output buffer will always push data to the first partition. The second output buffer will push data to the second partition, and so on and so forth. By the end of the day, when you finish scanning through all pages from the input file, you end up with b minus 1 partitions of your input data. Is that clear? Of course, it goes without saying, you do this hash partition on the grouping attribute, because the purpose is to evaluate group by aggregation first. But at the end of the day, what you can claim about those b minus 1 partitions? Well, what you can claim is records with the same grouping attributes will guarantee to be in the same partition. Of course, you may have collisions, meaning that records with different grouping attributes may also end up in the same partition. Because if you know you have no collision, then that's an easy case. You can already do a linear scan for each partition and do your group by aggregate already. But unfortunately, you may have collisions. Follow me? So you may have for the argument's sake, let's say these are the 3 partitions you have produced. Okay? So you may, observation number 1 is record with the same grouping attribute will end up in the same partition. In other words, if you have 9s in this partition, it's impossible for you to have 9 in any other partitions. You follow me? In other words, if 7 is here, it's impossible for you to have 7 here. However, you may have collisions, right? You may have 3, and you may have 7. You may have 5, and you may have 1 and 2. And that makes the case a little bit trickier than this case, right? If you know every single partition is like this becomes easy, right? If you want to do count, if you want to do sum, everything becomes easy because they all belong to the same partition. Same group. They all guaranteed to be in the same group. Notice that aggregation, by the way, the aggregation might not be performed on your grouping attribute. Suppose this is age. I may do count and sum on a different attribute. But that's okay, because as long as I have this case, I know these records will be guaranteed to be in the same group. So it's safe for me to just linear scan through them and compute the aggregate in a streaming fashion. Of course, over the aggregation attribute, whatever that is. Any question on this? Okay. Now, the challenge is how do you deal with these cases, right? When you do have collision. That's why we introduce another phase called rehash. The reason you do another hash phase is to reduce the probability of collision, right? I made this argument for you. If you have 2 hash functions, the probability of collision after hash 1 is 10%, let's say 1%. And the collision probability of hash 2 is 1%. If you hash a key twice in a row by h1 and h2, your collision probability will become 1% squared. Assuming 2 hash functions are independent from each other, which means you reduce the collision probability dramatically. And that's precisely what's going on here. What I'm going to do is, in the rehash phase, I'm going to take these partitions and turn them into my input. And what I'm going to do is, I load one partition at a time into my main memory. Because the goal is to reduce I/O, so I will load the entire partition into my main memory. Of course, by doing that, I have an assumption, which is each of these partitions is able to fit in memory, right? Fit in memory. And by doing that, of course, what is the condition that will make this hold? Well, we can do a simple calculation. Suppose you have n pages of input data, you partition them into b minus 1 partitions. So on average, each of them will have roughly this many pages. Okay? Of course, you may argue, this is the average case analysis. In practice, the distribution of pages into this partition might not be uniform. I agree with that, but if you assume you have a good balancing partition hash function, we can roughly estimate the behavior of the algorithm like this. If you have a balancing hash function, then roughly you're going to distribute these pages equally likely to all these partitions. Then you end up with roughly this many pages per partition. And given this, what does it mean by fitting memory? Well, that basically implies this must less equal than b. And this gives us the condition I showed you last time, which is n must less equal than square root of b. When this holds, I'm not saying it guarantees that, but very likely every single partition from your phase 1 will be able to fit in your memory from your phase 2. Do you follow me?
Would it be b squared and it's also equal to b squared?
Sorry?
Where did you get the square root from?
Sorry. Yes, that was a very good catch. That's a very good catch. Okay. Sorry about the typos. Okay. So once we understand that, let's look at the second phase, the rehash phase. I will load one partition into my memory. With this condition, most likely I'm able to do that. So I will load the entire partition into my memory, and then what I do? I apply another hash function h2, but here I simply denote that as hr, stand for rehash. It's an independent different hash function from HP, the partition hash function. Then I build an in-memory hash table for this partition. I build an in-memory hash table for this partition, meaning that I take this partition, I build another hash table for that, but now it's in memory. So most likely, I'm going to have this. Do you follow me? Chances are you may have this. You follow me? Meaning that you still have a clear, but the probability of this is very, very low. Do you follow me? Yes or no? But with this, now you can do your group by aggregate, because what you do is you simply do a linear scan of each of these partitions from this in-memory hash table, and to compute you aggregate on the fly. Because here is a key observation. Because your chance of clearing is so small, the number of running sums you have to maintain for the aggregate will be small. If you have 2 clearance per partition in this in-memory hash table, you only need to maintain 2 running sums while computing these aggregates. That's a critical observation, because you don't want to maintain too many running sums, while computing these aggregates, because they occupy space and you may run out of your memory. But if this number is small, like what we have argued, then you are fine. And furthermore, once you finish scanning one partition, you can safely output the aggregate for that group. Why? Because all records for that group must be from this partition now. Because it's impossible to see 5 from any other partitions from the first phase, and it's impossible for you to see 5 from any other partition from this in-memory hash table in phase 2. Combining these 2 arguments, all 5s, all records with value 5 must be here. So by the time you are here, output. can output, of course, for 5. To be precise, for group 5. Okay? So that's the rehash phase. Of course, there is this unlucky case where even if, first of all, if this condition doesn't hold, obviously you cannot expect all partitions to be able to fit in memory. Some of them will be, some of them will not. But even if this condition holds, you may still have the rare case where one partition is slightly bigger than your memory. And you have to, you're not able to fit the entire partition in memory, right? And what do you do in that case? Well, what I said in last lecture is you simply recursively call the same procedure. By viewing, let's say this partition, let me arbitrarily change my case here, change my input here to have like that, which is much, let's say this is bigger than E. What I do? Well, for these guys, I go to rehash. And for this, what I do? I view this as an input and simply call this two-phase hashing algorithm on this recursively. You follow me? I simply call the same algorithm using a recursion call. I view this as not as my input. Do you follow me?
Would you need to use a different hash function for the first phase?
Good question. You can, yes, you do need to use a different hash function for the first phase. Why is that? Can someone argue that for me?
Otherwise, all will be entered in the same partition as they have used.
Yeah, if you use the same hash function from the partition phase, then these guys will be end up in the same partition. Then you never gonna reduce the size of the input, right? So you have to use another partition hash function while doing this recursion call. Excellent point. Okay. Okay, so that's the two-phase hashing algorithm. So there's analysis and all that stuff you can read on your own, but basically a summary of what I have said. Now, once that being said, you can translate this procedure into this operator interface I discussed last time with a hash then aggregate, where this hash is this two-phase hashing algorithm we just described. This aggregation is simply running aggregate in a streaming fashion during the end of the second phase, during the end of the rehash phase. Okay, so that's the implementation. But we can do better. We can actually merge. If your goal is to do group by aggregate, let me be extremely clear, right? If your goal is to do group by and aggregate, sometimes you do group by, but you don't do aggregate. You simply put that out, the grouping attribute, right? But if your goal is to do group by and aggregate, you can actually merge these two operators into a single operator called hash and aggregate, meaning that you compute aggregate whenever possible on the fly during the hashing steps. And I'm going to illustrate this operator using this picture here, and this is called hybrid hashing. Basically, you merge the rehash phase into the partition phase. Okay, so here is how this works. Actually, this is very straightforward. Once you understand the two-phase hashing algorithm, this becomes extremely straightforward. So what you do is this: you input data. You design a hash function called HH. Stands for hybrid hashing, HH. And this HH does the following. It maintains a main memory hash table of size k, meaning that you choose an integer value k. Let me call this here. So you maintain this is memory of set B, right? And from this set B memory, you drop out a set K buffer, meaning that this region is of size K pages. Is that okay? And what you left with is another B minus K pages. Do you agree with me? And for those B minus K pages, I'm going to use one for my input buffer, and another B minus K minus 1 as my output buffer. So you may argue this is size K, this is 1, this is B minus K minus 1. What about the stuff in between? Black holes. Right? Think about that as black holes. Okay? Now, this are your pages on disk. Okay. So I'm gonna load them one by one into input buffer. Same drill, right? Same drill as what we have been doing. Right? Keep in mind, once you have taken this database class, whenever you do a data operation, like open a file, read and write from a file, never read and write a single record at a time. You always read, you do buffer read, buffer write. Right? This is simple. This simple trick will give you significant performance improvement already. Okay, you do buffer read and buffer write. So you reading one page, and then you apply HH. But now since data is in main memory, you apply HH for each. You apply each, you grab each record, and you apply HH on each record in turn, right? One by one. Okay, you hash one record at a time. Of course, hash on the grouping attribute. And how does the fundamental question is how does this HH works, right? HH works. Okay, I'm gonna write it out right here. One, if two conditions are true, right, it's equal to 1. Condition 1 is, of course, I need to supply a key. I call this region, what do I call this? I call this my in-memory buffer. In-memory hash table. I call this region in-memory hash table. I call it, so I use T to denote this region. Okay? I use T to denote this region. If X is in T. X in T, I will output 1. Or means X is not in T, right? But T still has space. Then I output 1. When I output 1, if it's 1, I will push X. Then X goes here. Then X goes to this table T. If it's 1, X goes to this table T. Okay? You see how this works, right? The reason I push X here is that either it's already there, and my goal is to compute a running aggregate for that group. And if X is already there, meaning that I will have an entry here, something like X equal to 100. Suppose you are doing count, meaning you have seen 100X so far. Or maybe it's equal to, I don't know, some random value, something. If like a sum, right? You are computing a sum over not necessarily X itself, but another attribute associated with all the record with value equal to X. and the sum so far, the partial sum so far is 178. And what we do is this record with value x will simply go and update this value. We'll update this value, maybe from 178 to 198. Suppose the record is x20 and you're computing sum over that second attribute. Do you follow me? And you push x to table t because if there's already entry there, it doesn't increase your space cost over t. If x is not there, but you still can push x over there if there is at least one space left, then in that case, suppose this is not x, this is y. In that case, I can simply use this entry to create a new entry for x and initialize that at x equal to 20. Without incurring any IOs. You follow me? And the step of figuring out which one I goes to is what I do. I push x to a hash function called hrx to decide which entry from this table t x goes to. That's kind of like my rehash function. Yeah? Okay, now, otherwise, what I do? Otherwise, I simply set hx equal to partition x. What does this mean? This means x is not in table t and table t has no space left. All k pages are fully utilized. There's no space left even for creating a new entry, a single new entry. Then what I do? I have to push x to a partition on disk and process them in the rehash phase. That's all you do. Okay? Yes or no? And of course, you may argue, wait a minute, your partition hash function has an output from 1 to b minus 1, but now you have b minus k minus 1 partition. What do I do? Well, that's easy, right? You can fix this by then this whole thing plus 1, that will give you the output range from 2 to b minus k as shown on the blackboard, on the slides. Yeah? And what's the benefit of this algorithm over this algorithm? Over this two-phase hashing algorithm? Well, sorry. The benefit is clear. The benefit is that in a lot of cases, you may not need to push any data to the disk partitions. In most cases, you are able to do everything in memory using this in-memory table T. Okay, using this in-memory T. And when that happens, when does that happen? When do you have a case where you will have no output to the output buffer and everything goes here? When does this happen? When does this happen? Can someone argue that for me? Right? Yeah. Huh? No? Okay.
When the number of possible root values is small.
When
The number of possible root
the number of possible group is small, so small such that
fits in that cache table.
such that they fit into this cache table K. And how do you formula this? Well, number of groups less equal than K times the number of entries you can fit in a page. Let me use, let's say, E for that value. E stands for number of entries fit in a page. How do you calculate that? Well, you use page size divided by the size of each entry. How do you calculate the size of each entry? Well, the size of your key for the group and size for the aggregation you maintain. That gives you the value E. And then from there you can calculate everything. Yes? Obviously there is a subtle trade-off. I don't know whether you guys realize this or not, which is I can which will reduce the number of partitions back to disk. There is this trade-off, right? Do you follow me? When k equal to 0, this degrades to the two-phase hashing algorithm. When k equal to b, cannot be b, right? At most b minus 2 because you have to at least one input buffer, at least one output buffer. When k equal to b minus 2, you go to this extreme case where you hope everything fits in the in-memory hash table, and whatever doesn't fit will go to a single partition on disk. You may argue, what's wrong for doing that? Sounds like that should be the way to do this all the time. Well, the challenge is, I'll give you a case. If you have a skew distribution, what we call a power law distribution. Do you know what's a power law distribution? You don't know power law distribution, just look at US income distribution. That's a power law distribution. And which is, this is the income. Let's say this is the per person income, right? How much money you get at end of year per person. And this is the US population. So number of people making this much money, number of people making this much money. Is that okay? And I sort them based on their income. So highest income go to the left, the lowest income go to the right. What do you expect this curve to be like? Let's see. What should I do?
Actually, would you have income on the bottom?
I should use, let me see, the curve. Most people will have very few income, right? So,
Do you want income?
0 minus 7, okay? Do I get it right? No.
Do you want income on the x-axis and then the
Yes,
frequency on the...
income on, yes. That's right. Okay, this will fix the problem, right? So this x-axis is dollars. And this shows number of people having X dollar per year. Now, what do you expect this to be? Well, I don't know, maybe initially, probably very few people have zero income, right? But quickly this curve goes like that. Right? You have very few Bill Gates, you have very few, I don't know, all those big names. Most of us like here, right? Some of us are fortunate are here. So this is what we call power law distribution. With this, what does happen? If you think about this, right, with power law distribution, you have this long tail. If you're unlucky, maybe these guys are the first one from your data file, and they all go to your in-memory hash table. And because they are so, the power law distribution, a distinct feature of that is a long tail. Meaning that these are not frequent, but doesn't mean you have very few of them. If you count the distinct value sense. They are not frequent, but the distinct number of them can still be a big number. So if you're unlucky, your data consists of these guys first. They will occupy your in-memory hash table. But it's a waste of your space because 1x, put it another way, 1x is the same as 1 million watts using this algorithm, cost-wise. And if you have a lot of such 1x, and they show up first, then you get scooped using this algorithm. If you go to the extreme case, because all of these guys will be pushed to a single partition on this, which is expensive to handle. Okay? So it's a delicate balance you have to consider. Now, pre-optimization. I will skip this later on. We will have a dedicated discussion on pre-optimizer later on. Okay. All right. That's all for single table evaluation. Any questions on this? Now, let me switch gear a little bit and go to. Go to the product 4. So in this product, you need to implement the axial merge sort. Axial merge sort. And what you do is you need to implement this sort.c file. So this is probably the easiest one you have got so far. There's one function you need to fill in. All right. So it's either than all. It looks like it's either than all the ones you have seen so far, but in reality, you actually have to fill in a few functions, not just one. If you look at the .h file. So this is the interface for that function you have seen. Right? So it has an input file, which is a heap file. Has an output file, which is the final sorted output. And you have int, length of int, which tells you the number of fields in an input record. Meaning, if you have a student record, student ID, first name, last name, then this value will be equal to 3. It tells you how many attributes a record has. And attribute type, which is an array of attribute type, the size of this array will be length of int. Basically telling you the type for each corresponding attribute for a given record. And this attribute type, this is an enumeration data type defined somewhere. If you do a graph, you will find it. It has integer, string, and things like that. And short, this array basically tells you the size of each field. And this gives you the information needed for parsing a record. First record is 8 bytes, first attribute is 8 bytes, second attribute is 10 bytes, and so on and so forth. So the size of this array will be the same as the number of fields you have. So this will give you the parsing information needed to fetch the value from a particular field. Okay? And the next one, field number, tells you on which attribute you are doing the sorting on. So obviously this will be less equal than the length in, the number of fields you have. Or less than or equal to that value. Then sort order will be either ascending or descending. Again, this will be an enumeration data type of 0 or 1. I think 0 is ascending, 1 is descending, something like that. And then this tells you, this is essentially the value B, the number of pages in your buffer. And so on, and status just tells you is passed in by reference, so you should set this value by the end of your call, function call, to either success or done or fail. Okay, that's it. So you need to sort it. And some facilitating functions you have. First facilitating function is make the heap file names. So in this product, right, the good news is the complexity of loading a page into input buffer and all that is being abstracted away from you, so you don't have to worry about that, through an implementation called scan.c. So that will basically give you a handle over an input heap file and ping a page for you and fetch a record, then fetch a record for you. So you don't have to do this step yourself. You don't have to interact with, in other words, you don't have to worry about interaction with buffer manager. It's done for you by the scan.c implementation. You understand what I'm saying? Otherwise, you have to worry about the interaction with buffer manager, ping a page, fetch a record. But this is abstract away from you by the scan.c, which I will show you right here. And this implement get next page and get the record and so on and so forth for you from a heap file. So it does the interaction with the buffer manager, so you don't have to worry about that. You understand what I'm saying? So all you need to do is use the scan class to keep retrieving record from a heap file. And it will ping the page and all that stuff for you. Okay? That being said, let's come back to this. That means that each heap file will be responsible for holding a run of data. So a run of data will be stored in a heap file. You still remember the concept run, right, from our discussion. So each run will simply be a heap file. Okay? And you want to have a way to distinguish different runs, right? That's the purpose of this hash function, which is to have a meaningful file name for each of these heap files so that you know this heap file is for which run and for which pass. Because you have pass 0, or phase 0, phase 1, phase 2, or you can call them pass 0, pass 1, whatever. You need to be able to distinguish, given a heap file, this is second run from pass 1, for example. So that's why you need to make a distinct name for the heap file. So it passed in pass number, heap file number, and name is passed in by pointer, which the value you need to set in this function. So by the end of this function, this pointer character array name will be set to a value holding the name of the heap file. And you can construct whatever heap file name you want, but basically your convention need to support your code to be able to decode this heap file is the second run from the first pass, something like that. One thing I want to remind you is, since all of you are using the same code, if you happen to run your code on the same machine and you happen to come to the same file name convention, you may run into a collision problem, right? So one way to make sure to address that is including your login ID into the construction of your heap file name. For example, Feifei -P1, pass 1, R2, that means pass 1, run 2, but for Feifei. So that will guarantee you will not have collision with anyone else. Question?
Do you mean collision when you guys test? Because if we're testing, it should be under each of our home directories, right?
No, not really, because you don't control the disk manager here. You don't know where this heap file is written into. By default, Mediabase write the heap file to temp folder /tmp. All of you, if you run on the same node, they all are written to the same temp folder. You follow me? Okay? So just make sure that happens. And pass number is like pass 0, 1, 2, 3. Run HF number, what is that? That basically tells you which run it is. Run number 1, run number 2, run number 3. So you will call this function from your merge step, right? From your merge step. Whenever you are ready to produce a run at output, you call this function first to produce a file name for that heap file before you're producing data to that run. And this heap file will be holding data from that run. Okay? So first pass will take the initial input file, which is your data, and the number buffer page as input, and produce what is the output. The output has two parts. One is the third parameter over there, which is the number of runs in the output, which is passing by reference, which means you should set this value by the end of this function. And this number of heap files as a result of running this function. Right? Essentially what you do is you load a buffer number of pages in and sort them and dump to a run. That's essentially what you do. And you may wonder, how do I do the sorting here? Well, good news is that's also given to you for different attribute type as well. So you don't have to write this sorting function yourself using this qsort algorithm. And there is even an example given to you, shows you how to use this qsort procedure to sort data of different types. So basically you load these many pages, then you simply call this qsort to sort them and dump to a heap file. That's it. And there is an example given to you as how to do that. Just follow the same example. You will be able to do this very, very easily. You follow me? Okay, so there's an example of this. Now come back to this. So now that we're done with first pass. What about the following pass? Well, the following pass taking the number of parameters that input. One is path number, which tells you which path you are currently at. This is useful for constructing the heap file name. Okay? That's the sole purpose of this. You need to know which path you are at in order to construct your heap file name. And OHF number, the number of runs from the last pass. Total number of heap files from the last pass, which is total number of runs from the last pass. Buffer number, again, size of your buffer. And new HF number. A new number for the number of heap files at output, passing by reference, which is to be set by the end of this function call, which means you are merging OHF number of runs into new HF number of runs. That's all you're doing. And in this function, you will call this procedure called merge. What it does is, okay, what does it do? Well, you take buffer number minus 1 number of pages, one for each run, and put them into what we call this scan array. Note that scan array is an array of scan pointers. I explained to you earlier what the scan pointer is. Scan pointer, each scan class is a wrapper around the heap file for you to read and write data from that heap file. So you have buffer number minus 1 number of scan pointers in this scan array. Right? What does it do? Well, it is essentially the cursor for each run. If you can think about it like that. How about that? And the good news is this is simpler than the algorithm I discussed in class, because the scan class, as I mentioned earlier, has abstracted away the complexity of loading a page from this run and fetch the next record. It's all abstracted away from you. You simply worry about this scan pointer. It will do the dirty job of pinning the page, bringing the page from disk to buffer and all that for you. You can abstractly, you can think about this as a pointer to the next record from each heap file. And so how do you construct this scan pointer from the following path function? Well, you make this many scan pointers, one for each run to be merged. Then once you have done that, you call this merge function, passing in these scan pointers you have constructed in the following path function. And run number, this integer tells you the size of this scan array. How many runs you are currently merging. That's what the run number does. And heap file star is a pointer to a heap file. What is that? That's a single file for holding the output run. You're merging this run number of heap files into a single output heap file. That's what this merge function does. So the following path will initialize the necessary objects for this merge function and call the merge function. That's it. Finally, the merge function needs to do the merge, right? And how do you do that? It uses this last function called pop-up. What it does is, using the scan pointers for each input heap file, which is an input run, it copies the next record from each run into an array called record. So this first attribute here, first parameter here is a byte array for not just a single record, but for run number of records, one from each run. So the merge function will copy the next record from each of the scan pointer and place that into this record array, and then call the pop-up function. Do you follow me? The run number has the same meaning. Tells you how many records potentially you have from this record array. In the worst case, you have run number of records from each run. The only subtle thing is this run flag pointer, integer pointer, which is a pointer to an array, to an integer array of size run number. What's the purpose of that? Well, the purpose is to tell you whether you have a record for a given run or not. Because during the merging phase, initially you will guarantee to have a single record for each round, for sure. But sooner or later, this is no longer true, right? Because the cursor move at different speed. Some cursor move really fast, some cursor move slowly, depending on the values of record from those corresponding rounds. So some rounds may have exhausted all records, meaning you finish merging those rounds before the other rounds. Then at that point, when you call this pop-up function, the number of records in the record array is no longer equal to the number of rounds you have. Yes? But what happens is what happens is this round flag tells you which round has a record in the pop-up array. If it's 1, meaning if the first one is 1, meaning the first round has a record. If the second is 0, meaning the second round does not have a record, and so on and so forth. This tells you whether a round has a record in the record array or not. Okay? So that's the purpose of round flag. Finally, round ID percentage passed by reference. The pop-up function, once you have this parameter as input, the pop-up function will check the record from this record array using the round flag array, then decide which record has the smallest value. If the second record has the smallest value, then this round ID will be set to value of 2. Since it's passed by reference, so merge will call this pop-up function, and by the end of the pop-up function, merge knows that, oh, the second round has the smallest value, which is the record to be pushed to the output buffer, output round, which is the new HF, the output heap file. You write a record to that heap file. Okay? That's it. Okay? And of course, once you do that, you need to update the pop-up record array for that round. Only for that round. The other rounds stay the same. Then you keep merging. That's it. So this actually, once you understand the procedure, in my opinion, this is a very simple one to do. Much easier than the buffer manager. A little bit difficult than the first one, but should be less difficult than product 2. Definitely much easier than product 3. Okay? All right, let me come back to our lecture. Okay, table evaluation. Group evaluation. So we talk about single table evaluation, and we are left with pretty much multi-table evaluation. If we know how to do join, we can pretty much feel safe to claim that I know how these SQL queries are executed within an engine, right? So let's look at multi-table evaluation. So before we move on to multi-table evaluation, let's just do a quick recap of the single table evaluations. Essentially, it boils down to how we can evaluate these relational operators. Okay? This brings us back to the first thing we have seen from this class, which is the relational algebra. We have selection, reduction, join, set difference, union, and aggregation. Okay? Of course, this is not available in relational algebra, but in a relational engine, people actually introduce those notations in relational algebra so that input SQL query will be translated into a relational algebra representation for reasoning and evaluation purpose. Okay. And this goes back to the same old concept we mentioned, that relational algebra is closed, quote unquote closed, meaning that I take a relational model as input and produce an output that's still described in relational model. This is critical because now you can pipeline this operator together. One example of that, to understand this, is, for example, with respect to the field of integer, the following operators are closed, which is, these are closed, but this is not closed. Because, for example, this cannot be described by the field of integer, but which means that you can pipeline this operator as much as you want, but not necessarily with division if your model is integer. Let me be clear, right? If your model is integer, you cannot pipeline this operator together. but you can pipeline these three operators safely in arbitrary order as you want, but not with the division operator. The relational algebra is closed in the sense that these operators, you can pipeline them in any way you want and still safe, meaning the output is always described by a relational model. And this is critical because this allows you to do query optimization. I don't know whether you guys realize this or not. Because of this, the engine is able to do optimization automatically without user input. It is because of this, because I can safely change the order, manipulate them, without worrying about producing something that's a monster that I don't understand. Right? So to facilitate our discussion, I'm going to use the same old example, have some sailors and reserves. Okay, good old friends. But now we're gonna, remember now if we look at what I said earlier at the beginning of the semester, I said SQL concerned about what you want, but not how to do it. You understand this better now, right? Because when you write SQL or even relational algebra queries, your sole purpose is to describe what you want, but not how to actually do it. Whether you are, for example, when you write group by and aggregate, you never need to specify, I want this to be done by sorting then aggregate. Or you can use a hash and aggregate. Even with hash and aggregate, you don't have to specify, I want to use two-phase hashing, I want to use hybrid hashing, I want to use hybrid hashing with size 100, k equal to 100 in memory buffer. You never need to worry about any of this. And that's the beauty of SQL and database system for a large part, which is user focus on what they want without worrying about how to get it. And this is critical, right? Because if you think about in business operations, right, your manager will tell you, okay, go make this report. He or she will not tell you, go make this report and do this and that, produce this report. By the time your manager has to tell you all these details like that, you need to worry about your job, right? Seriously. So that's a major strength of relational database system. But now in our discussion, we actually give you these numbers, these statistics values on the tables because now we are within the engine, right? Imagine you are sitting inside the engine, you are waiting for user query, and you need to execute this. And by doing that, now you need to worry about not only what to do, what the user wants, but also how to get what user wants. And this how part needs to know these statistical values, such as the length of the record and so on and so forth, to be able to make an informed decision as which plan, which way of executing this query is going to be more efficient. So that's why I'm giving you all these values. So for reserve, each tuple is 40 bytes, and you have 100 tuples per page, and you have 1,000 pages. For sailors, you have this setup, like what is shown on the slide. Selection, simple selection. Give you an example like that, and which can be translated into a relational algebra as shown on the slides. What's the best way to perform this selection? What is the best way to perform this selection? Well, the answer is it depends, right? It depends on whether you have indexing structure, and if you do have indexing structure, whether the selection condition match your index. We talk about the concept of match. What does it mean, right? The prefix of your index must be same as your selection predicate. The prefix of your index must be the same as part of your selection predicate.
Can you tell the management system to build an index for something, or does it just do it on its own?
Where those statistical values come from?
What's that?
Where those values come from, like the number of pages and what was your question? Can you repeat your question?
Just like can you tell the management system to build an index for this, or will it just do it when it?
The index. Well, when to build index? By default, most commercial databases will have a cluster index on the primary key automatically. By default. Literally all databases do that. Sometimes they will have a secondary index, meaning that unclusters index on foreign key as well. Why? The reason for that is the most common form of join in database is primary key join with foreign keys. And having index on primary key and foreign keys speed up those join operations by default. In addition to that, users can always tell the system to build different kind of index as you want. However, there are restrictions depending on the engine you are using, database engine you are using. A lot of them do not allow you to, unless you can tweak the engine, right? And change the configuration and so on and so forth. By default setup, a lot of them do not allow you to build a cluster index other than primary key. The reason is, at the time of setting up the table, they already built a cluster index on primary key, which means records are sorted by that. If you later on tell the system to build another cluster index on another attribute, this is a very costly operation because you're telling the system to resort the whole table based on that another attribute, which is going to be expensive if data is big. So a major responsibility of database administrator, a part of the job for a database administrator is to figure out what index to build and what index to maintain over time based on your workload. Okay? Now, come back to this. The best way to evaluate this depends on whether you have index, and if you do have index, whether the index match your selection predicate, and even if they do, whether it's what type of index you have, whether it's a B+3 or hash index, and what type of predicate you have, whether it's a range query or equality selection condition. Okay. And the other thing that matters is the size, the expected size of the output. You may wonder why this matters. I'll give you an extreme case argument. Suppose you have a B+3 index for a range query. Okay, on student table. And your selection condition is this. And you know, and you have, suppose you have a cluster B+3 index on age over students. Okay? And let me change this, right? Suppose your condition is this. And you know you have a cluster B+3 index on age over students. No brainer. Use B+3 to answer this query. It will be better than do a linear scan over student treated as a heap file. Right? Because the cluster index, very efficient. You search over the cluster index using this age less than 20, then you become a simple sequential scan in the data file, which is much better than scanning the whole file. You follow me? Now, if I change my condition a little bit, I change this to, and suppose I know this is a university student. Now, which is better? Well, still using index is better because you can use index quickly determine there are no students satisfy this condition. You can terminate. If you do a linear scan over the file, it's going to be very expensive. You have to look at all records before you can safely terminate. Okay? Now if I change my condition to this, what happens? Which is better now? Well, I will argue now, throw away the index. Linear scan the student's table is better than going through the index. Why? Because what you're looking at is and they are sorted by age, right? If you use index, most likely what's gonna happen is you're gonna do like that, then end up doing this. Or alternatively, I simply do that. I'm better off. I save those IOs of traversing through the index. You follow me?
That's like 3 or 4, right?
Which is nothing, yes, but for the argument's sake. And imagine if you replace this with a hash index or something like that. Right? You hash each record. Like if I change this to hash index, If it's a hash index, it makes perfect sense. I can use hash index to verify there are no records satisfying this condition quickly because I can simply hash what? Then I'm done. If you have a hash index. But if a condition becomes like this, if you use hash index, you're going to hash 5, 6, 7, up to, I don't know, 35, 40, 50 to be safe. But using a linear scan, you're not. My point is, output size matters. The reason I know this is going to be better than this is because I know at this point, your output size is big, such that everything is included and there's no point of using index whatsoever. So using this extreme argument, you can observe that output size actually matters. Actually, it matters a lot in determining which way of executing a query is better. Okay? Which way of executing a query is better. And that's why we have a special discussion devoted for this, which is called selectivity estimation. Selectivity estimation, meaning how many records you expect to see from the output compared to the input as a percentage of your input. If you have 1 million record as input and you produce 10,000 as output, then the selectivity is 1% in that case. Selectivity of that, in that case, is 1%. And once you know the selectivity, which is often called, also known as reduction factor, you can use reduction factor times the input to get a rough estimation of your output. And we will come back and revisit this later on. When we talk about join algorithms, you will see clearly why the output size actually matters. Because for join, especially for multi-table join, the size of the intermediate result determine which join algorithm actually will be more efficient. In order to decide which join algorithm to use for an intermediate result, you need to estimate the size of the intermediate result in order to make that decision. So the selectivity estimation is critical. I can give you another example, right? We just talked about this hybrid hashing algorithm, right? How do you set this value k? Well, you can argue that's kind of like a selectivity estimation problem, right? You want to estimate how many distinct groups roughly you have. That will tell you what's the proper value of k. Without either setting too little space for the in-memory hash table, or without setting too big a value, end up wasting space. You follow me? So that you can argue that's kind of like a selectivity estimation because size k roughly tells you the output size of your group by aggregation, because you're gonna have, if you have 10 groups, you're gonna have 10 outputs for a group by aggregation. And then you should roughly set your value k to be such that you can hold 10 entries roughly. So that's another example where selectivity estimation is important. Okay, we will discuss this later on. Selectivity estimation for a single table query is actually not that hard. It's actually trivial. But selectivity estimation for a join, even to this day, is an open problem. People don't know how to solve this properly. So let's look at simple selection. With no index unsorted heap file, well, you pretty much have no choice but do a linear scan, right? Do linear scan. And cost is simply n, the number of pages in the table R. With no index but sort, you can do binary search. You can reduce your cost by a lot, by basically a log of n compared to n. And in our earlier discussion of the cost analysis on heap file and sorted file, we said the cost for doing search on sorted file is what? Is log of the total number of pages plus number of matching pages. That's what we said back then, right? Now we know how to formalize this number of matching pages. We know that's essentially selectivity times the total number of pages. That gives you a rough estimation of number of matching pages. That's why you see this estimator over there. With the index on the selection attribute, you can use the index to find qualifying data entries, then for each data entry, you retrieve the corresponding data records. You can potentially do better if you have a cluster index and you have a range query. You don't have to retrieve every single data entry. Rather, you retrieve the first data entry and go from there to the data file and do linear scanning data file. So instead of retrieving every data entry, then from data entry go to record. You can go to the record directly and do linear scan over there. Okay? And to take a closer look at this, if we use index for selection, the cost depends on the number of qualifying tuples and whether you have a cluster index or not. You know, the cost of finding qualifying data entries typically is small, right? As you have seen from your midterm test, actually. Right? Whether it's cluster index or unclustered index, the cost of finding qualifying data entries is the same, whether it's a cluster or unclustered index. But if you go to find qualifying data records, cluster index and unclustered index has a huge difference. Yeah. There is an example of that. If we have a reserve relation, let's say we have selectivity is 10%. With a cluster index, the cost is little over 100 IOs. Why? Because I know the reserve has 1,000 pages in total. 10% selectivity tells you the output size is about 100 pages. That's exactly what I expect to pay because, like Monty had mentioned, the cost of traversing a tree is like only 3-4 IOs. So roughly the total cost is 100 also IOs. With uncluster, what will be my cost? If I know selectivity is 10%, I'm going to retrieve 100 pages, and each page has 100 tuples based on the earlier setup. 100 pages translate to about 10,000 tuples. With the unclustered index, I have to pay 1 IO per record. So my IO cost will be 10,000 IOs. Okay, do you understand where it comes from? This 100 and 10,000 tuple come from the fact that reserve is 100 tuples per page and 1,000 pages in total. If I have 10% selectivity, that gives me 100 pages, and 100 tuples per page for 100 pages give me 10,000 tuples. And the reason for this is explained by this figure here, which we have discussed in detail, so I'm going to skip this. Okay. What about general selection condition? Right? We talk about, so far the selection is a single predicate, right? Age less than 5, age greater than 20, or things like that. What about you have a general selection condition like that, which is a combination of multiple selection predicates? First thing what we'll do is we convert that into something called conjunctive normal form. How many of you heard CNF, conjunctive normal form, before? You should have learned this from your discrete maths class, right? Conjunctive normal form. What it says is, given an input predicate, you can always convert this to a collection of predicates. Such that for any Ti consists of only Ti can be expressed as small t1 or as ni number of predicates where Tj, each Tj is what I call atomic predicate. Meaning that Tj has no and or condition involved. It's a simple predicate. So this is what we call, and this form is what we call conjunctive normal form. Conjunctive normal form. Do you follow me? Any condition can be transformed into a conjunctive normal form, which is a collection of terms AND together where each term is expressed using a collection of ORs, where each predicate in the end is a simple atomic predicate. Do you follow me? Conjunctive normal form. Okay? That's why this condition is expressed as this. The condition above is transformed into CNF of this. And this is your T1, and this is your T2. And T1 has 3 small t's, small t1, small t2, small t3. And T2, big T2 has, again, 3 small t's, small t1, small t2, small t3. Matching that expression over there, I have just written out. You follow me? Yes? Okay, so that's CNF. Now, with that being said, we're going to discuss the case. I'm going to simplify the discussion a little bit. Later on, then I will talk about how to handle OR conditions. For now, I assume that my term T is converted into a CNF of the following form, which is and what's the difference between this and that? Well, I'm using small t now, meaning that I express my condition into a conjunctive normal form where each is an atomic predicate, and they are being AND together. In other words, there is no OR condition involved. Of course, this is not the general case, right? It does, for example, it does not handle this case I showed here, but we have to start from somewhere, right? We start with this base case. You follow me? Then we talk about how to handle the OR case. You follow me? Yeah? That means that I'm essentially looking at terms like this, A equal to 5 and B equal to 3. That's a conjunctive normal form of that form. It's a conjunctive normal form with only atomic predicates. Yeah? So this is the case I'm currently discussing. Okay? How do you handle this case? How do you evaluate selection over this? Well, this introduces this concept, I believe I mentioned briefly earlier, but let me now formulate this, which is the concept of match. Concept of match. We say an index, in particular, let's look at B plus 3 first. Then the same definition applies to hash index as well. We claim a B plus 3 index matches a conjunction of terms that involve only attributes in a prefix of the search key. Give you an example. If I have an index on ABC, this matches this term. Why? Because this term involves only prefix of the search key. What is my search key here, by the way? A, B, and C. Note the language used here involve only attributes in a prefix. It doesn't say it is a prefix of your search key. These two are different, right? There's a subtle difference. It doesn't require you conjunctive normal form to be a prefix of your search key. It only requires your conjunctive normal form involve attributes from your prefix key. From the prefix of your search key. What does it mean? Well, I'll give you an example, right? If my search key is ABC, if my CNF is A equal to 3 and B equal to 5, this obviously is a match because it involves attributes from only a prefix of my search key. By the way, what is my prefix? My prefix is, you can build a trie over your search key. This is the trie, right? In this case, it's a single chain, right? But in general, trie can be like, if you have A, B, C, and A, B, D, that's a trie. But so now it's a single chain, right? Because it's a single search key. This is a prefix, this is another prefix, this is another prefix. So your prefix is A, AB, and ABC. Okay? Those are the prefix of your search key. Let's look at another syntax, which is my question is, does this match the index? The answer is yes. By this definition, it is yes. Why? Because it involves attributes in prefix. These attributes, so what you do is you check is B and you do the same check for A. You follow me? This is different from saying the term must be a prefix of your search key, because if I define my definition like that, this will be no match because it is not a prefix of my search key. It's B and A. B and A is not a prefix of ABC. The takeaway message here is, I'm running over time, so let me stop after this thing. The takeaway message is the order, because we're using C and F, the order of your search predicate doesn't matter. Because this can be the same as. That's why in the definition of match, I only care whether you have attribute involved in my prefix or not. I really don't care about the order you have in your expression. So that means that why we care about this concept called match, because once we know there's a match, your index will be potentially useful for evaluating this query. If you have no match, forget about your index. It's not going to be useful for your search at all. Okay, so we will continue from here on Thursday.